Good morning, everyone. Uh, so my name is Tung from IBM Research Tokyo. So today I'm honored to present our work on ONNX-MLIR. So it is an open source compiler that bridges ONNX models and the LLVM ecosystem using MLIR. And this project is a collaborative effort involving many contributors from around the world. And I'm here to representing the machine learning team, and I would like to acknowledge their contribution. So this talk, I will walk through the architecture, design decision, and recent development. So ONNX-MLIR is a compiler. So just take the model in the ONNX format, and it compile them into optimized binary for AI inference. So basically, ONNX model are the graph, computation graph, and its one is used for model exchange. So we would like to provide a backend for deploying this model efficiently. And so this framework is leverage MLIR framework to perform high-level transformation, and LLVM to perform low-level optimization. So thanks to LLVM, so we can generate code from a wide range of hardware, such as x86, ARM, IBM machine, and a custom accelerator. So this project started at the IBM Research in 2019 and has since grown into an open source community. So with over 100 contributors from multiple companies. And it's also academically recognized with nearly 90 citations. And it's now used in production and research environment. So let's talk about the design goal of ONNX-MLIR. So our first goal is to define a reference ONNX dialect in MLIR. So ONNX is well known for AI inference, and it defines the common operator for AI, and is used in many enterprise AI workloads. So we wanted to make the compiler easy to write the optimization at the various level of abstraction from high level to low level. And MLIR is a perfect fit for this purpose. And next, we focus on the ease of deployment. So we provide a standalone driver runtime support in multiple programming language, such as C, C++, Java, and Python. So because of this, so we can easily integrate the AI into existing application. And finally, we build a set of testing for making the compiler robust and correct. So we have a unique step for every operation, ONNX operation, and every ONNX model in the model zoo. So the compiler is continuously tested on different architectures, operating system, and programming language. So this is the compilation pipeline in ONNX-MLIR. So we have several levels of abstraction. So the first one is the DNN, deep neural level. So in this level, we define the computation as a graph. So that's why we have the graph optimization here. So the next level is a loop and core. So basically, we describe the computation at a loop, and we have a loop optimization, such as tiling, skewing, and transposing. And after that, we lower to the standard dialect in MLIR. It is R5 and standard. And finally, we lower to LLVM. And then we use LLVM tools to do the low-level optimization and generate the executable binary. So in summary, we in this framework, we propose two new dialects, ONNX and kernel. And then I would like to introduce them. So the first dialect is ONNX dialect. So this dialect will represent ONNX operator in MLIR language. And we have an importer to import a model in the ONNX format into the MLIR program. So basically, one ONNX operator is imported into one MLIR operation. So in this case, we have mathmal. So we have ONNX.mathmal operation. And one ONNX graph will be imported into one function in MLIR. So we have a special operation, ONNX.entryPoint. So this is not ONNX operator, but we provide it to denote which is the main function in the generated executable file. And the ONNX dialect is automatically generated by a Python script from the ONNX declaration. So the ONNX declaration in the protobuf format, and we read the specification and generate the ONNX dialect. So this is one example of the ONNX operator in ONNX specification. So you can see that we have a name, operator name, and we have a short description. Then we have a version information, and what are inputs and outputs, and what is the type constraint for input and output. And this is a definition of the operation in MLIR. So for the description, this information comes from the specification, and then for arguments, they come from inputs, outputs, and type constraint. So you can see that we can have a lot of type here. And apart from that, we add the shape inference to the operation verifier and canonic equalizer. So basically, our ONNX operator has multiple versions. So we need to deal with multiple versions in the compiler. So for example, this is SQUEE operator. So it has 3 versions. So version 1 has one input, data, and one attribute. Version 11 is the same as version 1, but in version 13, the attribute now become an input. So it means that it is runtime information. So version 1 and 13 is quite different. And in ONNX-MLIR, we only support the lowering of the latest version only. So for the older version, so when we import it, so we convert it to the closest newer version. So for example, here we have 2 rewritten rules for SQUEE to convert version 1 to 11, and then 11 to 13. So later, if the ONNX added a new version, says 15, so we only need one rule to convert version 13 to 15. The next level of abstraction is loop computation. So and to express this abstraction, so we define the kernel dialect. So the idea is we want to separate the definition of the loop and loop optimization. So for loop definition, we have 2 operations: define loop to define how many loops we want to have, and kernel.iterate to iterate over a loop. So for the optimization, we can do the timing using the kernel.block and permutation using kernel.permute. So this is one example. The first one is we define one loop, and after that, for the third and 3, 4, and 5, we define the original computation. So we have a loop and scalar computation here. So the computation is based on the original loop. And in between, we can add arbitrary optimization. So in this case, we add the timing, so with the sign of 2. So this optimization, we don't need to change the original computation. So after that, kernel dialect will be lower into the F5 dialect. So you can see here in the F5 dialect, it generates 2 loops with step 2, so which is for timing. And there was one problem we face when generating code. So we have 2 places that require the same computation. So one at compile time and one at runtime. So for ONNX operation, we want to do the shape inference. So this is the compile time computation. And for this computation, we can generate the literal value or the question mark, mean the unknown value at compile time. But when we lower ONNX operation to kernel dialect, mean we want to allocate the buffer. So we need to compute exactly what is the output shape at runtime. So these 2 computations share the same calculation. So to solve this problem, we propose a kind of index expression class. So this is the polymorphic class that represents computation over shape. For example, we can do the addition, stealing, and selection here. And on top of this index expression, we define the shape helper for each operation. And this shape helper can be called at compile time at the 2-step shape inference or shape lowering. So depend on whether we give the builder to the class or not. So if we give the builder, it will generate the runtime code. Otherwise, it just generates the literal or and question marks. Yeah. So after that, we extend our compiler to support accelerator. And in IBM, we recently we have on-chip AI accelerator called ZAIU. This is an accelerator for inference. So it provides a high throughput and low latency inference. So to use this accelerator, IBM provides a library, IBM Z deep learning library, ZNN. So this is a very thin wrapper in C for the neural network processing assist instruction, so that we can use this not only for compiler, but other framework like TensorFlow or PyTorch. So given that compiler need a way to work with this library. And this is one example of the primitive in the library for addition. So you can see that the input and output in the format of Z-tensor. So this is a special layout that so that we can get the best performance with the accelerator. So basically, the work of compiler is how to prepare this Z-tensor and then call the ZNN function. So to support this accelerator, we propose 2 new MLIR dialect, Z-high and Z-low. So Z-high is a tensor-based representation of the ZNN API. So basically, it's the signature is similar to ONNX operator. And after that, we have a Z-low, which represents the low-level operation, so on the actual memory. And for Z-low, we can do the memory allocation and optimize the buffer allocation. So ZNN signatures are similar to ZNN API, and zero will be lower to LLVM core, so which will call the external function in ZNN library. Yeah, as I said, one important point to support the accelerator is how to prepare the Z tensor. So one requirement of the Z tensor is we need to keep the original shape of the tensor so that we can switch back and forward between the CPU tensor and accelerator tensor. So to do so, at the Z high level, we use the built-in tensor in MLIR, but we add the layout information. So in this case, it's 2D. So by using this layout information later, when we generate the membrane, we will create the ARC5 map correspond to this data layout. So if you look at the ARC5 map, you can see that the data is organized in a block of 4Ks, and the memory buffer is a 4K alignment. And because it's an open source project, so other than our IBM part, so we also have the other part, not ONNX to kernel, but ONNX to TOSA and ONNX to stable HLLO. So it's maintained by contributor from other company. For example, ONNX to TOSA now is used by AMD in their products. And ONNX to stable HLO is used by the ByteDance company. Yeah, actually, we don't have much information about the whole pipeline of the other part because there are many things they're not upstream just. But currently, what we have in the open source GitHub is lowering from ONNX to TOSA and from ONNX to stable HLO. So if you want, you can play with this. Yeah. So now let me share some story. So we have learned during the development of ONNX-MLIR. So the first one is about the memory buffer optimization. So initially, ONNX-MLIR, we have our own bufferization to optimize the buffer reuse so that we don't need to allocate them same memory again and again. But after that, MLIR introduced a bufferization mechanism. So, and we update our compiler to use this one. And at that time, it worked well. But after that, MLIR introduced a new bufferization mechanism. So, yeah, we want to catch up with the latest MLIR, and we update our compiler to use this one also. But after that, we found that the runtime performance was lost by 2x. Yeah, because we have a test for the ONNX model zoo, so we can know when some regression happened. And then we reported to MLIR. At the same time, we introduced a kind of compile flag to switch between the old one and the new one. So we still use the old one and observe when the new one is mature enough. And finally, the new bufferization has worked well. And then now we are using totally switch to the new mechanism. The second one is about the big constant. So you know, in the AI model, it become very big because of the learning rate, right? The computation itself is not so big, but the size of the constant are very big. So initially, we use a dense element attribute for storing the learn weight, because at that time, I mean, 4 or 5 years ago, what we have is a dense element attribute. And the memory consumption during compilation was really big. So it's increased after each constant folding. So at the end, the peak memory was 5 times larger than the model size. So our temporary solution was we allocate the buffer manually for constant folding. and only create the dense element attribute after we finish constant folding. And we can reduce memory consumption a lot, but it's still 2 times of the model size. And finally, MLIR introduced the element attribute interface that allow us to define our own storage for the attribute. And in the compiler, we create a disposable element attribute based on this interface. And so far, we quite satisfied with the memory consumption. So it's quite close to the model size. And finally, it's about the compilation time for AI. It's quite slow based on our observation. So this is one example when we compile the burst-based model. So this model has about 110 million parameters. So we have a multiple phase here, loading the dynamics, import ONNX model to MLIR, compiling and optimizing MLIR module. So they are using MLIR framework. But after that, we translate the MLIR to LLVM and generate a bitcode, generate object from LLVM. So we are using the LLVM tools like OPT and LLC. So you can see that for LLVM tool is 79% of the compilation time. So yeah, we just try to say exporting all the constant value to external file before calling the LLVM tool. Yeah, of course we know we will lose some optimization about the constant, but we can see that LLVM OPT is much faster. It's 2 times faster. But finally, they are still slow and consume a lot of time during the compilation. And during the development of ONNX-MLIR, we often interact with the MLIR community. Whenever we see any problem, so we want to upstream and contribute to MLIR first. Actually, we can do our kind of hacking, but it's better to submit to MLIR. So some issue like a big endian, because IBM Z is a big endian machine. So we have some improvement about memory normalization because the Z tensor is based on the using the R5 map. So we need to support the dynamic dimension and R5 loop fusion. So because our idea is express computation based on loop, so we really need to have R5 loop optimization. And of course, we actively follow and involve in discussion on our discuss forum. Yeah, that's all for my presentation, and thank you for your attention.
Any questions?
Yeah, you mentioned earlier that you have different IR versions, and I was just wondering if you have looked at the MLIR bytecodes, and if so, what's your experience with that?
Sorry for bytecode?
The MLIR bytecodes, I think it has some features to help with IR versioning, and maybe you haven't used it, maybe you use a different solution, but if you have, I'm wondering what your experience with that is, because I'm also looking at it right now.
Oh, I see. So actually, we are not using that low level of versioning control.
Okay.
So it's like, so ONNX operator is high level operation, right? Addition, multiplication. So different versions sometimes mean there are different number of input, like, or different number of attribute, and sometimes attribute become runtime input. So for that versioning, at the high level, we use a table gen. To just convert one version into another version. So normalize them.
Do you have literally like 2 operations, like add operation version 1, add operation version 2, kind of like that?
Yes, we have in MLIR, we have the SV1, SV2. So they are totally different. Actually, we have another option, like with a single operation, we add a version attribute, but it may introduce some problem. So we just splitting into a different operation.
Mm-hmm. Oh, okay, makes sense.
Yes.
I have a second question, if I may.
Yeah.
So you mentioned compilation time, and I was wondering if there are any MLIR passes that you found particularly slow. Mm-hmm. And just wondering, because I'm also looking at compilation time right now, and we found some issues with dialect conversion, for example. So maybe I'm wondering if you have similar experience.
Yeah, we this experience with the constant folding. Because for constant folding, we need to do computation at runtime. Compile time. Mm-hmm. So one thing we can do is we do the lazy computation. So if we do constant folding for transpose, right, then squeeze, then split. Actually, we don't need to do to create a new intermediate buffer. So we do lazily tracing the computation, and we create a new buffer only when we really want to have a computation, like an addition. That is one thing. So the other thing is we use OpenMP to parallelize the constant folding. So I think it's the most consuming computation during the MLIR combination.
Okay, thanks.
So I had a question about the also about the compilation time for the LLVM opt and these steps here. Yeah. Are you using Linux for that compilation, I would assume, or Linux?
Yes, Linux. Yeah.
Okay. Do you know exactly where the time is being spent in this? Actually, in the opt itself, is it just loading? Is it just working? Have we run profiles?
Unfortunately, we don't have such information.
All right, thank you very much.
Yes, sorry.
Okay, thank you. So during your presentation, I think I heard that due to the new MLIR bufferization, the performance was lost by 2 times.
Yes.
And I was wondering if you actually digged into the reason why, like why did the new bufferization create such a performance loss?
As I remember, it depends on the strategy to do the optimize the buffer allocation. So when we the idea is that we want to insert the allocation, right, at the right time. I remember at that time the new bufferization do the deallocation at the end of the program, but we want to deallocate immediately when it's unused. I guess so. Yeah. Okay. So later the strategy changed and we get a good performance. So of course, I think we can define our own strategy, right, but we are using the default one.
Okay, thank you very much.
Thank you. ONNX is ONNX has kernel dialects, and recently core dialects introduced a new ling-alg dialect. It seems that it is similar except for dynamic indexing you told them. And so actually in my job we're using ling-alg dialect as a front end. So I'm wondering that does ONNX-MLIR has any plans to integrate or something passes for supporting ling-alg dialects?
Yes, I think it's a good question. So we have a pull request still under development to switch to the Nino. But it's not active, just still at the pull request. However, if you want to generate a Nino, program. So you can go through the ONNX to TOSA path, right? And then from TOSA, it will go to MLIR.
Thank you.
So, yeah.
I'm curious where things stand with upstreaming ONNX-MLIR to the MLIR repository. Is that a good idea? Is that desirable? Is that something you're interested in? Would it make things better for the ecosystem?
So you mean upstream?
Well, ONNX-MLIR is in a different repository than the rest of MLIR. And so, I mean, that could be a good thing, that could be a bad thing, I don't know. One thing I've heard is that many people downstream that want to use it have many different dependencies, and then they all are all dependent on different versions of MLIR and things like this.
Yes.
Have you considered upstreaming it to MLIR itself, or?
Yeah, I think we always want to be upstream to MLIR. If it's maybe we need to have a conversation with the LLVM community to see how we do.
Yeah, so I don't know if it's a good idea or not. I don't know the
Yeah.
dependencies, but it would be great to discuss it. If
Yeah,
that's
currently
something.
it's belong to ONNX community under the ONNX community. I think the one problem is if we put it into the LLVM, right? And for ONNX, they often update the version. And then we need to frequently update that ONNX offset or ONNX version. I think it's the only problem I can think of now.
Yeah. Well, so again, I'm not.
Yeah.
I actually am too far away to know if it's a good idea or not. But
Yeah.
I think TOSA and some of the other border dialects kind of have their own like clear ownership that can steer it to align with the standard and things like this. And maybe it's something you could explore if you're interested.
Yeah. Yes. Thank you. Yeah, it's a good idea.
Any other questions?
Thank you for the presentation. I have a brief question. Recently, I guess a compiler the need of compiler optimization will be tools for dynamic optimization. For example, task parallelism. I think AI model becomes more complicated, and loop optimization is not enough for executing the AI model efficiently. So.
Yeah.
Is there any plan or internal discussions about task parallelism in ONNX-MLIR or your company? If you can open any information to public, please share your opinion.
Currently we are using the OpenMP to parallelize the program among the multiple CPU. So because in MLIR we have the OpenMP dialect, so from the kernel dialect we can add instruction to generate the OpenMP dialect. But if you want to run the multiple operation on different CPU, so currently it's not supported yet. Actually, sometimes we do something based on the need of the business. For example, for the AI model now, we see that it's go deeper rather than ladder, right, in a horizontal way. So it means that for the OpenMP, it may be more suitable. So far. Yeah.
Thank you.
Any other questions? All right, that wraps up our morning block. So thank you so much, Tung Lee.